Welcome to BGP Implementation and Tuning Part 1. Even though we are getting into the implementation and the configuration commands to do this, the concepts in BGP never end. We saw the initial concepts video, which was enough to lay the foundation of what BGP was, but we'll start off this video with a little more conceptual knowledge, understanding the difference between IBGP and eBGP, which are the really the two flavors that BGP supports. Then the rest will be focused on nothing but configuration with one key goal in mind, and that is to establish the BGP neighbor relationships. Once those are established, then we can begin exchanging routes between our BGP devices. Well, before we can get into the configuration of BGP, you need to have an understanding that BGP is more of a parent protocol to two subprotocols. IBGP and eBGP are the two flavors. I stands for internal, as in BGP running between routers under the same authority or in the same autonomous system. eBGP is external, or BGP that's running between different autonomous systems, two different authorities. Everything in BGP is geared around this concept of autonomous system. Autonomous system is, well, it's what it's been the whole time, is the IBGP world. When we had OSPF, we had all these areas connected together, and we said, oh, we've got, routers in all these different areas, and this is one big autonomous system because it's all under your control. But now when we're looking at BGP, autonomous system is kind of the foundation of everything. It represents all of the networks that are under an authority. Usually, your organization will be assigned a single autonomous system from the powers that be, the powers that assign autonomous system numbers. Now, there are public autonomous system numbers and there are private autonomous system numbers. We'll get more into that as we get deeper into BGP, but in this example, all of these are public autonomous system numbers, as in autonomous systems that would be valid and recognizable on the internet. So, IBGP is when you establish BGP neighbor relationships between two routers in the same autonomous system. We have a neighbor that is formed from this router to this router, and since they're part of the same group or autonomous system number, that means they will use IBGP. eBGP, I always think of the EBGBs when I think of that. That's where you have a neighbor relationship formed between two routers in different autonomous systems. That is most likely the kind of BGP that you'll use when you're establishing a peer with your ISP, because they'll have a different autonomous system than you. Not always, but most of the time. Now, one of the weird things about BGP neighbor relationships is it redefines what you might think of as a neighbor. When you were thinking of interior protocols, neighbors were just the things that were directly connected, right? Well, in this world, neighbors can be things that are not directly connected. Notice these two routers. They don't have a direct physical connection with each other. They're linked up through this router. Now, maybe you're running OSPF between these two routers, and OSPF right here between these two routers. This is an internal router. Maybe it doesn't have the memory to support the full-blown BGP routing table, so that's just one of your internal core routers. Well, IBGP relationships can form through the routers. And this is a weird paradigm shift I need you to make. BGP is like an application. It sort of rides on top of whatever network infrastructure you already have in place. So you could be running OSPF between those peers, you could be running RIP, it doesn't really matter. BGP rides on top of your existing internal structure. BGP does not usually replace an interior routing protocol. It's really meant to establish relationships with the outside world. So why would you run IBGP here? Well, maybe these are two routers connected to two different ISPs. This could be ISP1 and this could be ISP2. This is your company. You have redundant routers, so if one router goes down, you don't have a single point of failure, and you have a redundant ISPs. Now you can run IBGP between those two routers, so these routers can share information on what the best routes between the internet service providers are. It can also allow routes to advertise in from this internet service provider through your network and then out to that internet service provider. You could also cause a routing loop. But all of that aside, IBGP is very commonly run between routers that are within the same autonomous system if they're connected to the outside world. The reason these different types of relationships are key is because different rules apply depending on the IBGP and eBGP relationships that you have. Now, they can also cause different sorts of problems inside of your organization. As I mentioned, usually organizations don't run BGP everywhere. So you might have, let's say you are Autonomous System 6000 over here. This is your company. You're running IBGP between these two routers, so they are exchanging internet routes. Let me show you the flow. Let's say this ISP, this is one of your ISPs right here, advertises a bunch of routes to you. Now that's going to flow over this router over here because it's not running BGP. It's just acting as essentially a transport to allow this neighbor relationship to form. So the route advertisement flows through that neighbor relationship. This guy just passes it just like it's an application. It doesn't look at any of that data. And when it's received by this router, it goes, oh, your BGP update. I'll add you to my routing table and then advertise you out to this eBGP peer on this side. Now, likewise, this ISP on this side will send a bunch of routes in here to you, and that will flow through that same squiggly path and reach this ISP up here. Now, at that point, you would be known as a transit autonomous system because the ISPs are exchanging routes through you, which means that they will end up using you as essentially a path to reach each other. Now, here's the problem. Let me give just a brief example here. Let's say this ISP has a network of 12.1.1.0/24, and that's one of the updates that they send into you. So you're going to receive that, traverse the squiggly line. This router doesn't hear a thing about it. It passes up here to this guy. He goes, oh, great, the 12.1.1 network. So he knows about it and passes it up here to this ISP. Now, that's all the BGP. That's all in the routing table. Now, let's say there's some user up here that decides, I want to reach 12.1.1.5, which is some server on this network right here. Now, what's going to happen is it's going to come to this router, pass to you. Now, remember, this is application data now. They're saying, I want to reach that server maybe with web, port 80. So I want to get there. This router says, oh, I've got traffic for 12.1.1.5. I've got a next hop IP address of this router over here. So what it will do is pass the traffic to this router. It will say, hey, I've got, coming from the source of, this guy up here, whoever he was, going to a destination of 12.1.1.5. And this router says, exactly what I've got right there. Huh? What's 12.1.1.5? I don't know about the 12.1 network because I'm not running BGP. You've created what's known as a black hole in your network. This becomes a black hole for all the BGP traffic because it doesn't know about the BGP routing table. At that point, you have two choices. One, you can redistribute your BGP routes into whatever interior routing protocol you're running. Let's say it's RIP. You can send, just using redistribution, you remember the advanced routing topics we talked about, the BGP routes into RIP, so this guy will hear about them via RIP and know what to do with them. Now, the problem with that strategy is the BGP routing table can be how big? Hundreds of megs. Do you think the RIP protocol is designed to handle a network of 10 megs versus 100 meg routing table? No way. OSPF can't do it. EIGRP can't do it. If you dumped a full BGP routing table into an interior protocol, it doesn't matter what kind it is. It's going to blow up. It's not designed to handle a routing table of that size. So unless you're doing a partial route update or just a small subset of routes, it's very unwise to redistribute BGP routes into an interior protocol. Instead, what I would do to fix this problem is bring up a WAN link between these two. Have a direct iBGP connection, or your only other alternative would be to run BGP on that back router right there, because then it will know about the same routes that are coming in, which means that back router has to be able to support the memory requirements of BGP. So that's one of the issues that can happen with BGP peers. And that's, just one of many things that we have to consider when we're laying out our topology. With that initial understanding of iBGP and eBGP, I'd like to start jumping into the configuration. We're first going to set up the BGP process, then start configuring BGP neighbors. Now, as I mentioned before, BGP neighbors are manually configured. They are not auto-discovered like all the other protocols that are out there. And in this scenario, you can see that I have two autonomous systems. On the left over here, I have autonomous system 5500. On the right is 6500. Now, we're going to pretend that this is us. Over here on the right-hand side is our ISP, or our network that we're connecting to with eBGP, because that's another system. And I'd actually like to begin this whole process on router 5 because it's very simple. I don't want to get into the complexities of our own internal network before we actually just do a base BGP configuration. So I suppose in this case, it's a little odd. We're configuring the ISP. The way that we set this up is we go into global configuration mode, and just like any other routing protocol, we type in router BGP followed by an autonomous system number. Now, looking back at our diagram, we are autonomous system 6500, so I can bring that up here, 6500, enter, and the process starts. Now, as soon as I do that, BGP is up and running on this router. It's like a big power switch in the background has been turned on. And I can't make it a member of any other autonomous system. Like if I put 6501, it's going to say, sorry, you're already in 6500. It can only be in one autonomous system. From here, I have started the BGP process, and I can now begin the neighbor relationships. You're going to find the vast majority of your commands in BGP begin with the statement neighbor. Just about everything that we do starts with neighbor because it's all about tuning and tweaking individual neighbor statements. So I'm going to type in neighbor followed by what neighbor address I'd like to link up with. Now in this case, that's going to be router 4, which is 10.1.45.1. That's the serial interface that is connecting these two routers. So I'll put in 10.1.45.1. That was right? Right. Followed by a question mark. Now it comes up with a giant list of commands, and you can see why most of our commands start with neighbor. This is just about everything that we can do to modify the neighbor relationship, but it all has to start with this. The remote autonomous system number. You can't really type in any other commands dealing with the neighbor until you begin the neighbor relationship. So I'm going to type in neighbor 10.1.45.1 remote AS and what remote autonomous system number they're in. So I'm going to come back here. They are autonomous system 5500. So I'll put in 5500, hit the enter key, and we have our first neighbor statement in on the ISP router. Now nothing's going to work until the alternate side is configured. We have right now router 5 attempting to send open messages over here to router 4, but it's not going to work. And I can do a show BGP, and actually summary is the command I'll use. Oh, and when I said that, I meant IP BGP summary. And you can see that right here I have my first configured neighbor from router 5's perspective. You can see that there's the neighbor IP address, the version of BGP, the remote autonomous system, all the messages received, sent, all of this. You can see it's all dead. And you can see up, down, never. It's never come up. Now you can see right here the state is active. Now I want you to think back to EIGRP. Some of our early terms when we were looking at the videos was active and passive. And I said active is bad because that means it's actively trying to find a backup route. And when we're talking about BGP neighbor relationships, think the same way. If you see something is active, that means it's actively trying to start a neighbor relationship with that. And unfortunately, it's not working because it's staying active. If it's a good relationship, this should just be a number, which means it is receiving prefixes. You'll actually see the sequence number of the database that it's received. So let's hop on over to router 4 and get the mirrored relationship going and set up the other side. I'll put it in router BGP 5500 because that is router 4's autonomous system number, followed by neighbor and 10.1.45.2 is router 5. 10.1.45.2. Remote autonomous system is going to be 6,500. So I'll bring that back up. 6500. Enter. We now had the mirrored neighbor relationship established. And I should be able to come back and type in show IP BGP summary. It can take some time, so I'm not expecting anything yet. And look at that. We have currently neighbor is configured as idle, meaning it hasn't tried to start the neighbor relationship yet. We want to see that eventually move into active. And by the way, this is one of the things you have to get used to with BGP. Remember I said it was designed to be a slow protocol? I meant it. This is designed to be a very slow protocol. I've seen it take about 60 seconds for neighbors to come up at times. 60 seconds. For those of us that are used to dealing with things like OSPF and EIGRP, that's an eternity. And a lot of times we'll start, oh, you see that right there? The neighbor just came up. A lot of us will start doing troubleshooting, clearing sessions, debugs, and there's not really a problem. It's just BGP is slow. This is especially true if you're using this series to prep for the CCIE course, where you have a time limit that's assigned to you that you have to complete things in a certain amount of time. You get very nervous very quick when it takes that long for a neighbor relationship to come up. Let's hit the up arrow and do a show BGP summary. You can see that we now have been up for 27 seconds. Prefixes received, 0. Neighbor relationships can be established in BGP without actually sending any information between the neighbors. It's a weird protocol to get used to. First off, just statically configuring the neighbors is weird. But if you think about it, imagine the ISP's peril if BGP would auto-discover neighbors. That means that any one of their customers could bring up a router, run BGP, automatically peer with them, and then start injecting routes that would goof up their routing table. You can't have that. So in order to establish a BGP relationship with your service provider, you have to work with them. They have to statically configure you as a BGP neighbor. If they don't, you're not going to establish that neighbor relationship. So that was an eBGP neighbor relationship. Now let me show you iBGP. The only difference is that the autonomous system number is going to be the same between the two routers. It's not like I have this special iBGP command I type in. It's just when I type in my neighbor remote AS and the router sees that the remote AS is the same autonomous system as itself, it's going to go, oh, well, I guess that's iBGP. Now, I also want to talk about your internal network, or our internal network here on the screen. We've got router 4 and router 1 that are going to be our BGP peers. You can see those are going to be running BGP, whereas these other two routers are just running OSPF. I'm doing this for a reason. I want you to see that BGP neighbors do not need to be directly connected. The iBGP neighbor relationship can form through that network. It can move across the OSPF routers just like an application riding on TCP port 179 and be received by these two routers exchanging routes, and who knows, router 1 could be connected out here to some other autonomous system. The scenario doesn't fill it in, but I do want to prove that we can establish that neighbor relationship. So I'm sitting on router 4 and I'm needing to establish a neighbor relationship right here. So let's bring up the term prompt somewhere. And I'm going to go back under the BGP process. I'll do router BGP 5500 because that's my autonomous system. Under there, I'm going to type in neighbor followed by the IP address of my neighbor. And I can see that this one is going to be, well, which IP address should I use? It's a good question. And this actually is leading up to something that a lot of people struggle with BGP, and that is where to establish that neighbor relationship. Should it go to this IP address? Well, if it does and this link goes down, then I'm doomed because that IP address will no longer be available. And same thing, if it goes to this IP address over here and that link goes down, well, then my neighbor relationship fails. I designed a redundancy in this network for a reason, so which IP address should I use for a neighbor relationship? The answer is neither. I shouldn't peer to either one of those. I know some of you might have been thinking, well, why can't you do both? Well, you can't establish a dual neighbor relationship, meaning two neighbors from the same router, because otherwise you're going to be passing all the routes twice. It'll see router 1 as some kind of separate neighbor. The way that we configure this kind of network is to use loopback IP addresses. Let me show you how I'm going to set this up. On router 1, I'm going to create a loopback interface and give it the IP address 1.1.1.1. Windows Vista is doing this new little, you see this little thing here going on? The little thing? It's really messing up my writing. So I'm going to, I'll put 1.1.1.1. So that will be the IP address I give to router 1. Router 4, I'm going to create a loopback interface. I'm going to give it 4.4.4.4. I'm saying it so you know what I mean, right? I'm going to figure out a way to turn off that little loop that pops up somewhere in there. But that's going to be the loopbacks that I create. Then I'm going to advertise those into OSPF. So all the routers will know about them, allowing router 1 to reach them. Then I'll establish the neighbor relationship with the loopbacks rather than establishing it with the physical interface. As long as one interface is online, that loopback will be reachable. So it'll look much better in the example where my Windows Vista doesn't goof up my pen here. I'm going to back out of the BGP process. I'm on router 4, so I'm going to type in interface loopback, and let's just make it loopback 4. IP address 4.4.4.4. I don't know if you've ever done this before, but I usually use a subnet mask of all 255s when I use a loopback address like that. It's known as a host route. That way I don't, use 255, 255, 2550 and eat up the entire 4.4.4 subnet. I'm just using an individual IP address. I'll exit back out and go under router OSPF1 and type in network 4.4.4.4 area 0. At that point, I'm advertising that loopback into the OSPF domain. I'm going to jump over to router 1, which is in the upper left corner over here. I'm going to do the same thing over there. First, I'll do a show IP route, see if we're receiving that advertisement, and we are. We are now able to reach, 4.4.4.4, which is our neighbor across the way. I'm going to go on here and do a interface loopback 1. Assign the IP address. Advertise it into OSPF. At this point, router 4 should be able to see the one network. OSPF is very fast, unlike BGP. So I should be able to ping, and I always test before I do, the IP addresses of those loopbacks. Now I'm back over on router 4, so we can now move into the BGP configuration. I'm going to go under router BGP, 5500, and I'm going to type in neighbor 1.1.1.1, which is that loopback IP address. Remote autonomous system will be 5500. But we're not done. This is where a lot of people get stuck. They establish the neighbor relationship by typing that command in, and they do the same thing on the other side. Let me do that real quick. Get into router BGP 5500, and I'll do neighbor. I'm so used to typing in that network command. Neighbor 4.4.4.4, remote autonomous system 5500. That establishes the IBGP relationship, but the problem is the relationship will never form. I'm going to type in show IP BGP summary, and you can see that that is at active. And this time, it's not just because BGP is slow. It'll stay at active because it will never establish. Here's the problem. Router 4 will use one of its interfaces as the source address when it goes over to router 1. It'll use OSPF to find the best way. It'll say either that interface or this interface will be the source IP address, and I'm going to go establish a neighbor relationship with 1.1.1.1. The problem is when this router, router 1, receives a message that's coming from this is the source or this is the source, it's going to say, well, who are you? I don't have a neighbor entry for you. I have a neighbor entry for 4.4.4.4. I don't know who 10.1.34.2 or 10.1.24.2 really is. So what we need to do is we need to go in and add an extra command under our BGP process. Go to router BGP 5500, and I'm going to type in, again, it's going to be the neighbor command, neighbor 1.1.1.1 from router 4's perspective. And I'm going to type in update source, right there, if I could highlight it, followed by what interface I want to use as my update source. I'll put loopback 4, which is what I chose on router 4. Now I'll jump over to router 1, do the same thing here. I'm already under the process. I'll just hit the up arrow, neighbor 4.4.4.4, update source, loopback 1 on router 1. Now when they try and establish a neighbor relationship, and now it is related to the slowness, excuse me, the slowness of BGP. When they try and establish that neighbor relationship, it will work because it's coming from the right source IP address. That's one of the essential commands to do if you're ever using loopback interfaces. Tell you what, I'm going to clear off all that gibberish. I'm going to go into Windows Vista, figure out how to turn off this little bloop thing it does. I don't know what else to call it, and then come back so I can write cleanly again. All right, I think I got it fixed, I hope. So what I've done is redrawn it to just show the loopback interfaces that are being advertised in there. And in the meanwhile, our neighbor relationship came up. You can see that router 1 now sees neighbor 4.4.4 is up, so it's moved from that state of active over to a state of just a prefix number, how many prefixes have been received. So we've got now an eBGP relationship. We've got iBGP relationship that's going across the entire network and not a directly connected neighbor. Let me just do a show IP BGP, which shows the BGP routing table. Notice, it's empty. This is what's weird about BGP, is that the neighbor relationships have been moved completely separate from the actual network commands. Remember, when we did every other routing protocol, RIP, OSPF, EIGRP, every single routing protocol relied on the network command. We would type in the network command, this, that, and the other. And that will establish, and that will tell the routing protocol which interfaces it should establish neighbors on and which interfaces it should advertise into the process. In BGP, the network command is just which networks to advertise. The neighbor command tells what neighbor relationships to advertise. So it's very weird to see neighbors that are up with no BGP information being received, no BGP networks being advertised. We'll actually get into advertising networks in the upcoming nugget. There's one more thing I want to show you, and that is this scenario. We've got router 4 connected to router 5, and I just showed you how you can use loopback IP addresses to communicate between iBGP neighbors. But what if we had redundancy in place, meaning we had a second WAN link that was going between router 4 and router 5 that we use for redundancy, or maybe even load balancing. Maybe these were two T1 lines and you were just using IPsec load balancing to send, packets down both of them. Well, you'd do the same thing. You would create loopback IP addresses on both router 4, and your ISP would have to create one on router 5. So let me do that. I was thinking I'd just tell you about it, but I want to show it to you. I'm going to jump over to router 5. I'll do interface loopback 5, IP address 5.5.5.5, all 255s. Now, most of the time, an ISP and a customer will not run an interior gateway protocol between each other. So there's no way that the customer will know about that loopback they just created, nor will the ISP know about this loopback on router 4 without some sort of advertisement going in there. And what most people will use is a static route. In this case, on router 5, I don't have a redundant link, but we'll pretend that I do. I'm going to go into the global config mode and just do a static route. I'll do IP route 4.4.4.4. And the next hop address will be 10.1.45.1, which is the other end of this WAN link. So that allows router 5 to reach the loopback on router 4. And let's make sure that we can get there. Sure enough, we can. I'm going to come over to router 4 and exit out and do an IP route to reach 5.5.5.5. Go to 10.1.45.2, which is router 5, the highlighted interface that I have up there. So now I should be able to ping 5.5.5.5. And that's most of the time what the ISP and the customer will do. However, they'll actually create two static routes, one to reach 4.4.4.4 going on one of those interfaces, one going on the other. And as soon as you create two equal cost static routes, The Cisco router does the rest. It will automatically load balance between both of those anytime you're going to between those destinations and utilize both T1 lines. Now here's the problem. I can set up the neighbor relationship to use 4.4.4.4 as the source, just like we did with our internal peer here, and they can use 5.5.5 as the source, but the neighbor relationship will not form because there is a rule. eBGP relationships must be, by default, directly connected. DC. You got to have router 4 directly connected to router 5, which you might be looking at and going, well, it is. But when you're communicating between loopbacks, it doesn't see it that way. It sees those loopbacks as being one hop away, meaning router 4 literally has to go through router 5 to reach that loopback interface. And likewise, router 5 has to go through router 4 to reach its loopback interface. So what we come to is yet another BGP neighbor command, and that is known as eBGP multi-hop. Let me bring up the terminal window. On router 4, I would actually go in. I'm not going to do the whole configuration because it's pretty easily explained. I would go in and I would remove the neighbor relationship with router 4's direct IP address and replace it with the 5.5.5.5 loopback that I just created and created the static route for. I would then put the update source to be my loopback interface. So router 4, when it communicates with router 5, it will end up using this 4.4.4.4 IP address to speak rather than using its directly connected interface, just like we did with the iBGP peer. Then, after we configure the loopback update source, we follow it up with this command. I go into the routing process, and I would type in, if I can get back under the routing process, I would type in neighbor and my new neighbor relationship that I created, and here's the command, eBGP multi-hop. I then specify how many hops away that neighbor is, meaning essentially how many routers away it is. In this case, I would put 2. It's assumed to be at 1. Like, I just get there, it's 1 hop away, or I should say directly connected. eBGP multi-hop will allow the neighbor relationship to have establish up to 2 hops away. I could put 50 to say that eBGP neighbor is 50 hops away. I can tune and tweak it, but you got to be careful because it can also lead to loops in the network. Meaning that if you have redundancy, maybe HSRP or some redundant setup that you have going on and the hop count is too far, you might end up going around an autonomous system, through another autonomous system, all the way back around to the same router because you put the eBGP relationship too many hops away, or you allowed the flexibility to be too many hops. So usually I'd recommend, even though they let you go to 255, whew, that's far away, I would recommend going no more than 5 hops. Well, that's enough information for one video. But at this point, you should have a pretty good understanding of how to establish those BGP neighbor relationships between the routers. So to hit the high points, we did talk about iBGP versus eBGP, the real difference being, are you forming relationships within or outside of your own autonomous system? We then set up the BGP neighbor relationships using the neighbor remote AS command and followed that up with the update source command to use the redundancy, creating the loopbacks, and the eBGP multi-hop, allowing us to have the redundancy even with our external peers. I hope this has been informative for you, and I'd like to thank you for viewing.